afternoon. So, as usual, the plan for the week. Today we continue on 6LoWPAN, so we see which are the features introduced by the 6LoWPAN standard. And if time allows, we will also switch to 6LoWPAN routing. So today we just focus mainly on the adaptation features of the 6LoWPAN protocol stack. And let's say either today or tomorrow we will continue with the routing, how routing is approached in 6LoWPAN. Okay, so I mean this full week is dedicated to 6LoWPAN, I would say, protocol. Okay, so just to wrap up from last time. Last time we stopped somewhere around this slide, which you see, which is actually showing which are the network architectures which are supported by 6LoWPAN. Okay, so just to focus on what 6LoWPAN is. 6LoWPAN is basically the alternative to ZigBee to provide internetworking protocols to sensor networks. Okay. So, what kind of networks do we have in under 6LoWPAN? We have something similar to what we have seen in ZigBee, so 15.4 kind of networks, which is called the simple low PAN. Okay, which is composed of a bunch of nodes, which are distinguished in between routers and hand nodes. Okay, and we also have an edge router there. Okay, so just to complete the analogy with 15.4, the nodes which are called edge here are leaf nodes or end devices in the ZigBee jargon. What we call here routers are basically the ZigBee routing devices or ZigBee routers. Okay. And the edge router is something similar to the ZigBee coordinator or the PAN coordinator. Okay, that's the analogy. Which are the differences here? The main difference, if we just focus on this simple low PAN topology here, from 6LoWPAN to ZigBee, is basically in the role of the edge router. What do I mean? What I mean is that the edge router in 15.4 usually implements some kind of protocol translation, meaning the PAN coordinator or the ZigBee coordinator speaks ZigBee underneath, meaning in the ZigBee network, okay, and speaks something else up to the internet. Okay, so it's a real gateway. A gateway between two different kind of worlds. Here, this edge router is somehow transparent in the sense that the protocols which are used, the communication protocols which are used downstream, so from the edge router down to the network devices, and upstream, so from the edge router to the internet, are all the same, which is the IP, okay, the internet protocol. So the architecture is the same as in ZigBee, okay, but the functional roles of the edge router is fundamentally different than the functional role of the ZigBee PAN coordinator or the ZigBee coordinating device. Okay, this is the most important difference between ZigBee kind of architecture and 6LoWPAN ones. Okay, why so? That's very simple to understand, because 6LoWPAN, let's say, pushes down to the sensor nodes the very same protocols which are used in the internet, which is something I've told you several times now, right? And this allows to have basically a transparent kind of architecture without any translation or translating gateway device. Okay? Then out of this simple low-PAN architecture, you have more, let's say, involved architectures like this one, which is called extended low-PAN, low-power network. where basically you have multiple bubbles, multiple simple LoWPAN, okay, which are managed by different edge routers. Okay, and these two edge routers, for example, they might be connected to some kind of backbone or backhauling technology. Okay, this is kind of similar to what happens, for example, in Wi-Fi deployments, in 82.11 Wi-Fi deployments, where you might have different access points, Wi-Fi access points, okay, which are connected at the back end to some kind of technology, such that even if you move from one access point to another, you're always connected to the same, it's called SSID, right? So if you move from here with your smartphone to another room, you're always connected to Polimi Wi-Fi network or Polimi protected Wi-Fi network, even if physically you connect to different access points, okay? And this kind of service is implemented by, or better, using an architecture which resembles the one you see in the slide. Okay? And the same stuff happens in 6LoWPAN. And then you have what is called an ad hoc LoWPAN, where basically what is missing is the gateway to the internet, the edge router. Okay, so you have a kind of floating low power personal area network, which is basically standalone. Okay, clear so far? Questions? Very well. So this is basically the same things which we have already commented on. Okay, the additional information on this slide is basically on the integration issues. Okay, so to support all the architectures which I showed you in the previous slide, I need to have some kind of adaptation or integration features. Okay, why so? Because even if ideally the protocols which are used to transfer information in this kind of part of the network with respect to the upstream part of the network are the same, you always have IP. Okay, as I have already told you, the kind of IP which is used in the internet, okay, needs to be adapted to, let's say, make it usable also in the low power personal area network. Okay, which means that somewhere in between, most likely here or here, you must implement some kind of adaptation or integration functionalities to, let's say, handle in some way the translation between the plain IP in the internet to the IP spoken in the wireless sensor network world. Okay? And today we will focus mostly on the adaptation features. Okay? Yes. So basically, if you have a look at the stack, the protocol stack, which is placed where this integration happens, so for example at the edge router has a kind of double stack in the sense that it speaks on one side plain IP. For example, it has its own physical layer, its own medium access control protocol, and it speaks plain IPv6. On the sensor network world, which is the right-hand side of this stack here, you see that you have your own physical layer, which is 15.4, you have your own medium access control, which is 15.4. On top you still have IPv6, but you need some kind of adaptation, because IPv6 does not fit very well into 8 to 15.4 medium access control. Okay? So these adaptation functionalities or integration functionalities are basically defined in this very thin adaptation layer, which is called LoWPAN adaptation layer. Okay? Questions? So what kind of adaptation features do we have in that thin layer? We have two of those. The first one is header compression. As we will see, IPv6, which is on top of here, okay, has a very long header, okay, header with a big size, which does not fit very well into the limited size of the layer 2 PDUs, packet data units, frames. So we need to compress reduce, to code somehow this header such that it can fit in a kind of lossless way the layer 2 frames. And by lossless, I mean that the same information which is conveyed by the original header, okay, can be reconstructed also after compression. Okay, that is called lossless kind of compression. And the second functionality is fragmentation. So as I probably have told you already last time, since we might have long IPv6 packets up to 1200 bytes, and since we have short layer 2 frames up to 127 and something bytes, we need to have some devices or adaptation functionalities which handle the fragmentation. So which takes the original IPv6 packet, slice it down into chunks, different chunks, such that each chunk can be fitted into one layer 2 frame. Okay? Then you have a bunch of additional features which are though not directly part of that adaptation layer, but still they are part of the 6LoWPAN stack, and most of the feature deal with routing. So as we will see, besides this, let me go back to slides. Besides this tiny adaptation layer in the 6LoWPAN stack, at the same layer of the adaptation layer, you have a routing kind of layer, which is, let's say, the normal way to go also in plain IP, where you have IP, and aside IP, you have all the routing protocols like AODV, like RIP, like OLSR, and so on. Okay? Which are not physically handling the transport of information, but they are actually handling how information is transported. So along which ways information is transported. Okay? So this is just to underline that this is not the full 6LoWPAN stack. What is missing here is routing and all the signaling protocols which are used to make 6LoWPAN happen, so to make it work. Basically. Clear? Okay, so let's take a few slides to nail down what IPv6 is. Okay, how many of you have heard about IPv6? How many of you have studied IPv6? In which courses? Okay, high school. So, anyone here studied IPv6 in some courses at Polytechnical? Okay. Okay. So let's say 10 minutes, no more than that, to see what IPv6 is, since it's at the basis of 6LoWPAN. Okay. Such that you can also appreciate what kind of adaptation features are implemented by 6LoWPAN on top or underneath IPv6. Okay. So basically, just to cut it very short, the IPv6 is just redefining the Internet Protocol, which is nowadays mostly version 4. The main novelty is basically the restyling, I would say, of the IP packets, and at the same time the restyling of the IP addresses, which are the addresses used to route traffic in the internet. I should have said first the restyling of IP addresses and then restyling of IP header, but you understood, right? The idea is that the 32-bit addresses of version 4 are no longer, let's say, sufficient enough to address all the devices which should be connected nowadays to the internet. Okay, they're actually over. Actually, 2 years back, the last chunk of IPv4 addresses was signed. Okay, so nowadays we don't have any free IPv4 address to be assigned. Okay. So what I did to counteract this problem was to, the different things. Okay, but the most disruptive one was to introduce IPv6, which is just increasing the size of the IP addresses, bringing IP addresses from 32 to 128 bits. Okay, so to increase the addressing power of IP addresses. Then, I mean, this kind of restyling has impact on the IP packet format. Okay, because we cannot reuse the same format we had in IP version 4, so we have to, or they had to define brand new IP headers, for example, IP packets. And then IPv6 also comes with additional kind of features which are kind of underneath when you speak about IPv6, but still they're important ones. The most important ones are basically improvement in how addresses are assigned. Okay, how do addresses are assigned in IP version 4? What's the assignment procedures of IP version 4 standard IP addresses? How do you get your IP address you're using for connecting at your place or even here? Okay. Suppose that this authority has done its job and you have a chunk of IP addresses. Okay. How do you, final user, end user, get one of these IP addresses in a classical kind of ways? How do you do that? Do you have your own IP address which you bring with you when you go out for a beer? Printed on your t-shirt? No, right? So you use different addresses depending on where and when you connect to the internet. Okay, so these addresses are assigned somehow dynamically through dynamic kind of protocols, like the HCP, the DNS, and so on. Okay. Still, all these ways in a classical kind of IP version 4 address assignment are centralized ones, in the sense that there must be some server, the HTTP server, okay, which tells you what address you will be using for the session you are just initiating. Okay? In IP version 6 is more or less the same, so there still is this kind of centralized entity to hand out IP addresses in version 6, but there are also simpler rules. Or better, there are also simpler ways, more distributed ways to have an IP version 6 address assigned. So just to be more specific, or the takeaway message here is that besides enlarging the IP address size, okay, IP version 6 is also redefining some of the rules which allows you to get one IP version 6 address. Okay, and in most of the, or in many cases, this assignment can be also distributed, meaning that you don't have to ask any longer to a centralized entity to get your own IP version 6 address. Okay. This is called stateless auto-configuration, because you don't have any control or interaction with any centralized kind of ways. Then there are some more features which have been added to the standardization, to the standard, the version 6 standard, which are not listed here, but which deal with security. What it means? It means that you don't have security embedded into IP version 4 protocol. Okay? Let me rephrase it. You have IPsec, which is another standard which builds on top of IP version 4, which allows you to encrypt your IP packets, so to provide security at the networking layer. Okay? But IPsec is not part of IP. It's not part of the standardization protocol called IP version 4. Okay? So what I did was to embed these security functionalities into the definition of the IP version 6 standard. Okay? Such that you don't have to rely any longer to external standards, external protocols. Okay? That's a formal difference. In practice, both protocols are secure. So IP version 4 and IP version 6 they're both secure. Okay. And the last comment on IP version 6 is basically the growth rate. This is an old piece of data back in 2009, but the annual growth rate is of 1400%. Okay, most of the so-called over-the-tops like Google, Amazon, Facebook, and so on and so forth, they already offer IP version 6 connectivity, most of them, to their services. So if you want, you can access, for example, Google kind of search engine, okay, by contacting an IP version 6 address or an IP version 6 enabled server. Okay. On the addressing side, I guess that's very simple and stupid. On the left-hand side, you have the IP version 4 address, and on the right-hand side, you have the equivalent or the corresponding IP version 6 address. The first difference is size, 32 versus under 28 bits. Second difference is how address is represented in practice. IP version 4 addresses are represented in 4 groups of decimals. Okay. IP version 6 are commonly represented in groups of hexadecimal characters. So this is the format of basically one specific IP version 6 address. Each character is to be represented as an hexadecimal character. Okay? And this is the translation between the hexadecimal and the binary stuff, basically. Okay? Which, by the way, is not correct because 2 is not this kind of thing. But anyways, okay. And that's 2 numbers, which just give you the idea on how many addresses we have available. Okay, 4 square meters. This is IP version 4, so 7 times 10 to the minus 6. There are 7 times 10 to the minus 6 addresses every square meter of the Earth surface. IP version 6, there are 10 to the 21 addresses for every square meter of the Earth interface. Okay, which is kind of enough to, or hopefully it will be enough to address most of the devices, at least in the next 50 years. Okay, who knows? Questions, clear? Okay, on the packet format side, on the packet format, up here you have the version 4 header. Down here you have the version 6 header. The first thing, which is clear at first glance, is that the version 6 header is much simpler. You have many fewer fields than the version 4. For example, you don't have any longer the checksum, you don't have any longer the several flags, and so on and so forth. Plus, source and destination addresses are shorter. Okay, I guess that all of you are familiar with this packet here, right? Are you? Yeah, let's do a quick test. What is the time to live field here? What is it for? In IP version 4. Huh?
Number of hops.
Okay, number of hops for doing what?
Hops to reach the destination.
Okay, better. Time to live is the lifetime of the packet in number of hops, meaning how many times the packet can be rerouted by a new router. Okay? What about the protocol field?
IPv4 or IPv6?
Huh?
IPv4 or 6?
That's the version field.
That's what
Like what? Okay, so the protocol is basically an identifier of what kind of information the IP packet is carrying. Either a TCP segment, a UDP segment, or an ICMP packet, or hence. Okay? And so on and so forth. So as I was saying, this is the IPv6 kind of header format, which has less fields, fewer fields. Some of those are taken from IPv4, some of those are brand new. Let's very quickly go through them, okay, because some of those will be relevant to the compression feature, so how to compress this header. Always remember that the first adaptation feature of 6LoWPAN is to take this header and try to squeeze it as much as we can. Try to compress it as much as we can. Okay? So the version field is the same as IPv4. This is the 6, representing the IPv6 version. Then you have two fields which are called traffic class and flow label, which are used to implement some kind of quality of service at the networking layer. And by quality of service, I mean differentiating different types of flows or packets. Okay? So basically, if you decide specific combination of these traffic class field bits and these flow label fields bits, you can enforce different priorities for the packet which is managed by the router. Okay?
Coloring.
Say again?
Like coloring and marking.
Yeah, kind of. Usually these fields here are then interpreted by routers which manage IPv6 packets by hacking a little bit the queuing policy. Understand? So you receive an IPv6 packet which has a given priority, belongs to a given flow, okay? And depending on what priority this packet has and what flow the packet belongs to, the router may decide to put this packet at the head of the queue, or in the middle of the queue, or at the tail of the queue, or even, if discarding is required, it may decide to implement some specific discarding policies depending on the contents of these fields here. For example, discarding with lower probability packets which have higher priority. Okay? Clear? Discarding is commonly implemented in routers. Why? Why do we need discarding in routers? Because we have limited queues, right? And we really want to be away from congestion. Because in packet switch network, congestion means that you have infinite delays. Okay? If a queue fills up, it means that your delay grows exponentially. Okay? If you have a congestion event, your delay grows exponentially. So you routers implement some kind of discarding rules. Most of those are also in advanced discarding rules. So they start discarding even if the queue is not full. Okay, just to avoid congestion. And the discarding policies are basically using the content of these fields to decide which packets to be discarded. Okay? Then you have a field which is called payload length, which is telling you exactly how long is the payload of the IP packet. Then you have the next header field, which is telling you what kind of header you have into the IP packet payload. And this kind of field here is kind of equivalent to the protocol field of IP version 4. So it's basically telling you what kind of protocol, what kind of information the IPv6 packet is carrying in the payload. Okay? And then you have the hop limit, which is exactly the same as the time to leave. So it's telling you what's the hop count limit of your IP. So let's keep in mind these fields, because now we will see how these fields are compressed in 6LoWPAN adaptation layer. To be 100% precise, the header compression functionality does not compress only the header at IP version 6 layer, but it also compresses the UDP header, because the reference 6LoWPAN communication stack is the one you see here at the right hand side. So basically you have an application, then you have UDP, you have your IP version 6 with adaptation functionality, And then down here you have your own physical and access control layer. And since UDP also adds up headers to the application information, the adaptation functionality at the IPv6 layer is also compressing the UDP header. Okay? Again, we are not compressing only the IP version 6 header, so this thing here, but we're also compressing the header which comes from the UDP. Okay? As you can see, we don't have here TCP, which is the other transport layer protocol in the classical internet, because again, it's too heavy. So that's it has an header which is too big. It has signaling procedure which are too heavy to implement it in wireless networks. Okay? Clear? Questions? Okay, so let's have a look at this compression kind of feature. So the first characteristic of header compression is that it is stateless. It means that it does not require the edge router which is reading, compressing or decompressing the packet to maintain its state. So to store local information which is used to decide how the packet is to be compressed or decompressed. So nothing has to be stored locally, okay? Because all the, as you will see, all the information needed to compress and decompress the packet is carried in line. So it's carried in the packet itself, okay? Again, why so? Because we don't really want to store any local information. Again, we have limited memory at the nodes, so we really need to make things as much easy as possible. And this means that we don't really want to maintain information locally. Second feature is that it's flow independent, which means that it's actually very close to stateless, but flow independent means that two packets which belong to the same flow may be compressed and decompressed in different ways. Okay? Which means that we don't want to maintain a state of the flow which belongs, the packets which belongs to which flow, okay? But we really want to compress packets independent of one another, okay? And then header compression is implemented first using some tricks or making some very obvious observations, and then implementing additional compression functionalities. Let's start from the tricks. For example, some fields of this IP version 6 header have no really use in wireless networks. So I don't really care that each packet is carrying the version 6 here. Why not? Because all the packets carry that version, right? You need this information where you have cross traffic, so where you have traffic which is mixed up between version 4 and version 6 kind of packets, okay? But if all the packets in your network are version 6, you don't really need to carry in each packet version 6, okay? Because all the packets are version 6. So, for example, this field can be elided, can be cancelled in the 6LoWPAN compressed header, okay? Then, for example, the payload length here, which tells you how long is the payload, okay, can be also elided, because if you remember, you have this same information already available at layer 2, at 15.4. In 15.4, frame format, if you remember, we had a field which was telling us how long was the frame, okay? Layer 2 frame is the payload of an IPv6 packet. So we don't really need to have here the payload length. Okay? Why is it here in classical IP? Why? So why do we need to have a payload length indication at the IP layer? General IP layer, classical IP layer. There are two reasons, I would say. The first one is that because IP is general and it can run in principle on top of layer 2 protocols which don't have a length indication field in their frames. Okay? Clear? So if this is not present at layer 2, it must be present at layer 3. Okay? And since IP may run also protocols which don't have this indication at the layer 2, we need to be on the safe side at layer 3. Second reason is that to avoid what is called cross-layering, meaning that what I've told you, so to elide this payload length because we know it by looking at layer 2 information, is a cross-layer kind of operation, in the sense that an information which is available at layer 2, which is the frame size of layer 2, must be made available at layer 3, at the IPv6 layer instance. This is called cross-layer. Okay? And this is not, let's say, it might be tricky, okay, in some cases, this cross fertilization of parameters between different layers. Okay? So the classical way to go is to keep layers separated, okay? Layered. That's where the word layer comes from. So basically all the information must be available at each layer to let that layer process the information in a meaningful way, without the need to go down and ask information to other layers. Okay? And then, for example, the other fields like the op limit, the source address, the destination address, and the next header and flow level and so on and so forth can actually be compressed depending on the context, as you will see. Okay, so in other words, version field and payload length are headers which are not there in 6LoWPAN version of IPv6. Okay, all the other headers, including traffic class, flow level, source headers, op limit, and so on and so forth, can be there or not depending on the specific context. Meaning they will be compressed or not depending on the specific context. Okay, and we will define this context in a few slides. Okay, before going to the context, as you can imagine, the highest contribution to the compression rate is provided by the source header and destination headers, because they are 128 bits each one. Okay, so we really want to compress as much as we can the source and destination addresses. And to do that, let's have a look at how these source and destination addresses are basically organized. So IPv6, just like IPv4, provides some kind of hierarchy in the address itself. In the sense that, as you remember, in IPv4 you have a part of the address which is dedicated to the network, okay, and a part of the address which is dedicated to the node in that network. The same stuff happens in IPv6, which defines the so-called prefix, whose length, let's say standard length, is 64 bits, and the interface ID, which is again in the default size of 64 bits. Okay? Just like in IPv4, the first bits, so the prefix, identifies the specific network you're in. Okay? The 64 bits of the IID, so the interface ID, identifies that node, a specific node in that network. Okay? And then there are a further classification in IPv6 addresses, meaning that given a specific IPv6 address, by looking at the address, you can, by scratch, classify the address of being either a unicast address with global or link local scope. We'll get to these two definitions in 1 second. You can soon identify the address to be a multicast address, an anycast address, or a loopback one. Okay? Again, going along the lines of the analogy with IPv4, these kind of classes are kind of resembling the ideas of classful addresses in IPv4, where you have class A, class B, and class C addresses. Okay? Clear? So, takeaway messages. You have a prefix and a postfix, or an interface ID in IPv6 addresses. If you look at the prefix, okay, your address can be in one of these 5 classes here: loopback, unicast with global, local, multicast, anycast, and so on and so forth. Okay. Just by looking at the unicast with the unicast addresses, unicast means addresses which are used to address nodes in a unicast way. Okay. You have 2 subclasses here. The first one is the global scope, which means that nodes which are outside the network of the sender, the IP packet. And the second one is link local, which means that nodes which are in the range of the sender. Okay? Just keep this in mind because we will use these concepts in the compression of the IPv6 header. Okay, so let's get to the compression. So how compression is implemented. So the first comment here is the following. Compression is stateless, which means that all the information which tells the node who reads the packet how the packet is compressed must be carried in line. So must be carried together with the packet which is transferred. Okay? So basically, given your IPv6 packet, what you do if you're running 6LoWPAN compression is to take your IPv6 packet, okay, add to the packet a bunch of bits, okay, which tell you how the packet is compressed. And the bunch of bits which are added to the packet is these kind of purple fields which you have here. Okay, so these purple fields here are the bunch of bits which tells who is receiving the IPv6 compressed packet how the packet is compressed. Okay, such that the receiver of these, let's say, fields here is able to decompress the packet. Clear? Which means that what you have from this point right is the compressed IPv6 header and the payload of the IPv6 packet. Clear? Is it clear? So these kind of purple fields here is called the header compression header. So it's a header which you add up to the IPv6 header to tell the processor of the packet how the header is compressed. Okay? It seems paradoxical in the sense that you want to reduce information and then you add bits to the information you want to reduce. But the trick is that the amount of bits you save here is much more than the amount of bits you have added with the header. Clear? Okay. So let's very quickly see how this works field by field. Idea is very simple. Idea is that to have in this header compression field, or header compression header, sorry, a number of fields which correspond to all the fields in the typical IPv6 header. Okay? For example, I have a field here which is called TF, okay, traffic class and flow label, which is referring to the traffic class and flow label field of the original IPv6 packet. Okay? I have a field here which is called next header, which refers to the next header field in the original IPv6 packet. I have a field here which is called the op limit field, which refers to the op limit count in the original IPv6 header, and so on and so forth. Okay? So you have one field for all in the header compression header for all the fields in the original IPv6 header. Okay? And the idea is that this field here, so the value of this field in the header compression header, is telling you how the corresponding field in the original IPv6 packet is compressed. Okay? Here. Okay, so let's see some examples. Okay? Let's start from the TF field. The TF is the field which handles the compression of the traffic class and flow label fields of the original IPv6 carrier. Okay? It's a 2-bit field, which means that you have four what's the name? 4 combination of these 2 bits. Okay? If this field is 0, it means that the 2 fields, traffic class and flow label, are not compressed, which means that they are carried in line. Carried in line means that I expect to find these 2 fields in the compressed header, which follows the header compression field. Okay? And then you have all the other combinations, like, for example, if this field is 1, you just have a part of the traffic class field, which is called ECN. That, you need to know it, plus the entire flow level field. If this is 2, it means that you just have in line the ECN and the other part of the flow level field, which is the DSCP. Okay, and if this stuff here, if this field here carries a value of 3, it means that you have nothing. Okay, so you don't have any information in the header here on flow label and traffic class. Okay, so the most favorable situation from the compression point of view is when this field here is 3, because you are basically eliding the traffic class and flow label fields from the original. Okay? Clear? Questions? Okay, and this happens basically for all the other fields. So if we look at the next header field, it's a 1 bit. 0 means that the next header field is present in the packet header here. 1 means that the next header is compressed, meaning that you have a header, a next header here, but it's compressed. Okay, and we will see how it's compressed if this kind of upper layer protocol is UDP. Okay. Then you have the hop limit field, which is a 2-bit field, okay, which is telling you what is the hop limit of the IPv6 packet. Okay, it's a 2-bit field, so for combinations. If this is 0, it means that you have an inline field, hop limit count field in the IPv6 packet here. If it's 1, it means that the hop limit is 1 here. So if it's 1, this means that you don't have any hop count limit in the header here, okay? But the hop count limit is set by default to 1. This means that this is a 1 hop kind of packet, okay? And then you have 2 more values. So if this hop limit is 2, okay, you have an hop limit of 64. Again, the hop limit is elided here, okay, and the receiver knows by default that the hop limit to be used is 64. And then the third case is 255. So basically, different combination of these 2 bits gives different scopes of how long this packet must live, okay, or can live, and correspondingly how much the header is compressed with what regards that specific field. Okay. Then the CID, SEC, and SEM, DEC, and DEM are basically fields which are used to decide how the IT headers are compressed, and we will see in a specific slide. So what I want you to remember is basically the principle rather than the meaning of all the fields. Okay, I have an IPv6 header. I want to compress it. I want to handle compression in a stateless way, which means that I have to add signaling bits to the packet itself to tell how the header is compressed. Okay, and these bits correspond in a kind of one-to-one way to the original fields of the original header IPv6 header. Okay. Okay, so this is basically what I already told you, fields by field. This is the TF field, so let me just skip it. This is the next header and the limit field, and let's get to the address compression. So basically, you have different address compression modes, I would say, which depends on the combination of these sec and sem fields. Okay. So if both sem and dem fields are 0, okay, it means that you have the full address in line. So you do not compress anything. Okay. Then, if you have sem and dem fields equal to 1, 0, 1, okay, it means that you're just eliding, meaning compressing, the 64 prefix of the what do you call it? Of the corresponding IPv6 address. So you're just moving away the first 64 bits, okay, and leaving only the remaining interface ID bits in the header of the IPv6 packet. If sem and dem are value of 2, basically, so 1, 0, it means that you are eliding more, so you are eliding 112 bits. So you are taking away from the headers, from the headers field, the first 112 bits. Okay. Then you have the usage of these sec and dec fields, which tell you whether the address compression which you are performing is, let's say, stateless or context-based, which means that basically, besides this three way of compressing the addresses, you may define different contexts, okay, by specifying, for example, okay, what is the amount of bits of the prefix you want to elide, okay, in your IPv6 header, okay? Clear? And this depends on whether the compression mode is stateless, okay, or is context-based, okay? So, idea is the following. You take these four fields in the header compression header, okay, sec, sem, dec, and dem, okay, and depending on the content of these four fields, okay, you can define different contexts in the sense that you can define different number of bits you can elide from the addresses you see in your IPv6 header. Okay? This context can be stateless, meaning the three contexts I showed to you, so either everything in line, or you remove 64 bits, or you remove 112 bits, or you can specify the context, okay, by adding here an additional bits field, 4-bit field, okay, to tell what the context should be. So to signal what should be the number of bits which are elided from the prefix of the IPv6 headers. Okay, we'll see some examples, so it might be more clear here. Then you have the multicast address compression, but you know it's, let's say, the same rationale as the one we have told for the unicast one. So let me just skip it. Okay. So what you have in the end is, I mean, what you see on the channel, the bits you see in the channel in the end is something which is shown in the slide. So you have the header, the 15.4 header here. Okay. Then you have this small field, which is the dispatch field, which is the first 3 bits of the header compression header. Okay. Let me go back a few slides. So these 3 bits here are given, and they're just used to tell the receiver that this is the starting point of the header compression header. Okay. This is called dispatch in the 6LoWPAN jargon. So you have this small dispatch stuff here. Then you have the header compression header at the IPv6 layer. Then you have the compressed IP version 6 header, according to what is written in this header compression header. Okay? And then, if the IPv6 packet is carrying the UDP segment, for example, and if the next header is compressed, you have the header compression header, which is referring to the UDP, okay, and the compressed UDP header also. And then at the very end of this chunk of bits, you have the data, the application data. Clear? So let's see, we have defined this HC1, so how this header compression header is handled. Let's see how this HC2 is defined. HC2 is the header compression header referred to the UDP. So it has the same function of HC1 in the sense that it is telling how UDP header is compressed. Okay? So let's have a look at the UDP header. This is the standard UDP header. You have a source port, destination port, length, and checksum. Okay. Just like before, what is a source port here? What is the use of source and destination port in plain UDP? What do you use them for? Huh? Okay. Exactly, to identify the specific application which is using the UDP transport service. Okay. Length is basically the same meaning as IP. It's giving you the length of the UDP segment. Okay. And the new thing with respect to IP is the checksum, which is basically providing an integrity check on the bits of the UDP segment. Okay. Again, the target is to compress this stuff here. Yes, it's 8 bytes header as much as we can. Doing it field by field. So we define an header compression field, which is the one you see here. Okay, and starting field by field, the first thing they are doing to compress the UDP header is just to limit the port number which can be assigned to application running on 6LoWPAN. Okay, and the idea is that all the applications which run on 6LoWPAN must choose a random port address in this range here, from 61,000 to 61,632. Okay, why so? Because this range of ports can be represented with only 4 bits, okay, and not with the full 8 bits as the original ones. Okay, so if we reduce the range of the ports which can be assigned, we can reduce the space, the number of bits which are needed to address that range. Okay, that's very stupid. Okay. Then length can be elided as well, because we are relying on top of IP version 6, which in turn is relying on 15.4. So we have all the length information we have from lower layers. Okay, so also length here can be elided. And then the checksum, we might decide to have it or not. Okay, which means that we can decide to compress fully the checksum by eliding it or not. So this is the header compression header for the UDP, okay, which has again a dispatch here, which is telling you that this is a UDP compressed header compression header. It has 1 bit for the checksum. 0 means that the checksum is in line, so it's not compressed. It's there. 1 means that the checksum is elided. It's not there. Okay? And the following 2 bits are the ones which tell you how much the ports addresses are compressed. Okay? So if these 2 bits are 0, it means that the 2 ports are, the source and destination ports are not compressed, they're in line. And depending on the value of these 2 bits here, you might decide to elide, to get rid of more bits of source and destination ports. Okay, 8 bits for the destination port if this is 1, 8 bits for the source port if this is 2, and 12 bits of both source and destination ports if this is 3. So again, the most favorable case is when this field here has a value of 3, which means that you spare 24 bits out of the original source and destination port addresses. Okay? Clear? Okay, so let's see some examples. This one is basically giving an example of the most favorable compression case where you have a link local communication, meaning an IPv6 packet which is meant from a destination which is one hop away from the sender. So it's a packet which is meant for a one hop neighbor of the sender. Okay, so communication is link local. The color code here, these orange fields, they are elided from the IPv6 header because they are derived from the lower layers. Okay, and then this light, what is it? Blue, or whatever, purple color here. It means that all the other fields are in compact form as specified by the header compression layer. Okay. So, for example, version 6 is in compact form, so it's not there. Traffic class and flow label are 0 because it's a one-hop kind of communication, so we don't really need to specify anything, okay, in terms of prioritizing traffic here. Payload length is not there because it's derived from lower layers. The next header is a UDP one because it's a UDP communication, okay. The op limit is 1 because it's link local. Okay. The prefix and the source prefix and destination prefix, they are all link local, so they can be elided. Okay. And then the source ID and destination ID, they can also be elided because it's link local, which means that you can use the medium access control addresses to just what do you call it? Reach your destination. Okay. And then you have the UDP header compression, sorry, UDP compressed header, source port and destination port. The length is not there, and the checksum, in this case, we decided to keep it. Okay, I don't know why, for some reason. So what it comes out is that you have an original 24 bytes header, summing up UDP and IPv6 header. Okay. And if you compress this header according to this kind of compression scheme, you can go down to 7 bytes, okay, which is kind of high compression gain. Okay. The other case is the global unicast case. The difference is that the source and destination of the IP packet are not link local, which means that they are different prefix, for example. Okay, so you cannot just elide the source and destination prefix because they are different. Okay, and you must keep some information on source and destination prefix. So the compression gain for source and destination prefix cannot be as high as the one we have seen before. Okay. So to cut it short, in this case, if you have to keep some context on source and destination prefix, the gain you have is a bit less than what you had before. Okay, so you go down from 48 to 12 bytes. Okay. Clear? Questions? Okay, so one disclaimer. You don't have to know exactly all these details on fields, compression headers, and so on and so forth. Okay? So what you have to know is just the main rationale and the main guidelines on how compression is implemented, meaning stateless and so on and so forth. Okay? So the second functionality which we see, which is fragmentation, we will just give an overview of it because it's pretty much the same as a plain IPv4 fragmentation and a plain IPv6 fragmentation. The idea is the following. In IPv6, I have a minimum required PDU just to have a full-fledged IPv6 packet, which must be higher than 1280 bytes. Okay. Still, we have much smaller containers at layer 2, so we need to fragment stuff. So we need to fragment our IPv6 packet to make those, let's say, fit layer 2 frames. Okay. This fragmentation is one of the adaptation features implemented in 6LoWPAN. So the idea is the following. I have my full-fledged IPv6 packet or datagram, okay, which I have to chunk, to slice it down into different fragments, okay. And fragmentation is implemented whenever needed just by adding to all the datagram fragments a fragmentation header, okay. So basically you take your data, you take your IPv6 packet, okay, you chunk it in, you slice it into a number of chunks, fragments, okay, and you send these fragments in one single layer 2 frame by adding to each fragment one specific header. So still I'm paying something in terms of efficiency because I need to define a header fragmentation header for each fragment, okay, but I cannot do any different because I need to fit the constraints posed by the layer 2 frames. Okay. So let's see what is this fragmentation header for. Fragmentation header basically must carry 3 types of information. Okay. Fragmentation header must be used to define what original IP packet to what original IP packet that specific fragment is belonging to. Okay. Second information is the size of the fragment, so how long is the fragment which is carried on. And the third information is what's the offset of that specific fragment with respect to the original packet. So whether it is the first chunk of bits of the original packet, the second, the third, and so on and so forth. Okay. And this is exactly the information which you have in the fragmentation header. Okay, fragmentation header, you have this field here, which is called the datagram size, which is telling you the fragment size in bytes. Okay, you have this datagram tag, which is containing the information on what original IP packet originated that specific fragment. Okay, so all the fragments of the same packet, they have the same datagram tag field. Okay, and the last piece of information is this datagram offset, which is telling where in the original packet, IP packet, that specific fragment is positioned. Okay, this is used for reconstructing the original packet. So by placing the bits of the fragment in the right position in the reconstruction buffer. Okay. Then in 6LoWPAN, difference with respect to plain IP is that this fragmentation header has a different format depending on whether the fragment is the first or not. Okay. In the first fragment, you don't have the datagram offset because that's the first fragment. So you don't really need to specify what the datagram offset is because it's the first fragment. Okay, and you recognize the first fragment by the value of this bit here, which is the bit of the dispatch of the header fragmentation header. Okay, all the other fragments have this datagram offset here. Okay, clear? Okay, that's very nice, so it's a very nice feature, but just like in IP version 4, it's scarcely used, so it's not used so frequently. Okay, and the reason is that fragmentation comes with an overhead. Okay, the overhead of having this fragmentation header for each chunk. Okay, and also because we always have to remember that we are working on lossy networks, so low power wireless network, which are characterized by high packet error rate, for example, so by high probability of losing one packet. Okay, which means that if you fragment your packet, okay, the probability that your original packet is correctly received is reduced, okay, if you fragment your packet in more than one fragment. Okay, so basically, what is done in practice, as we will see tomorrow or next week, is not to implement fragmentation at the IP layer, just like we have seen today, but to move up fragmentation at the application layer, such that the information which is generated by the applications which run on wireless sensor network, they give you from the very beginning data which fit basically 802.15.4 frames. So you don't need to fragment at the IP version 6 layer. Okay? The third reason why fragmentation is not used is that because it's computationally heavy. Always remember that you have to run fragmentation, or better, the devices who have to run fragmentation are edge routers or routers in general, okay? Which might be energy constrained and power constrained, processing constrained devices. Okay, so you don't really want to kill the processor of these edge routers by making him fragment too much data. Okay? Clear? Questions? Okay, so there is one last part of this slide set, which is about maintenance and management. So basically, we're not covering it here now because it's no use, in the sense that it's enough for this course to know what is it about without going into much details. So as you already know, the plain IP protocol works because there are protocols aside which provide basically signaling support and error control on IP version 4 kind of protocols. Okay, for example, the ICMP protocol, okay, is that layer 3 protocol which is basically used for troubleshooting or providing signaling support for the IP plane 1. Okay, so it's that protocol which defines packets and sessions to check whether one IP is reachable, okay, how far is this IP, and so on and so forth. Okay. The same stuff is available in IP version 6, and the same stuff is available also in IP version 6 for low power networks. Okay. The point is that just like it happens for plain IP, also the ICMP version 6, which is running in plain IP version 6 networks, cannot be reused as it is for sensor nodes. Okay, it cannot. And besides the main reason, which is, again, signaling overhead, the other reason is that all these signaling protocols always assume that a node, an IP address is on, is reachable. Okay? Because in the internet, in the IP, you always assume that one router is always on. Okay? This is not longer true in low power networks based on IPv6, because nodes can switch on and off depending on the specific duty cycle of your 15.4 kind of network. Okay? Which means that these signaling protocols like ICMP version 6 must be adapted, okay, in such a way to account for this discontinuous activity cycling of underlying nodes. Okay? So that's the main message I would like to convey to you with respect to this, neighbor discovery and kind of signaling support for IP version 6. Okay, we cannot use IP version 6, ICMP version 6 as it is. Reasons are too heavy. Second reason is it does not account for non-continuously on devices. So we need to do something on the procedure of ICMP version 6 such that it accounts for both problems. Okay? Again, we will not cover these slides here. Okay? Questions? Okay. So, since we have to change topic, I guess we can stop here for today. And tomorrow we will see how routing is managed in 6LoWPAN networks. Okay? See you tomorrow.